Hi, everyone. This is the Hungry Math Professor here, and thanks for coming to my channel. And today I'm going to do a review of this book, Philosophy of Mathematics in Antiquity and in Modern Times by Ulrich Felgner. Um, I enjoyed reading this book. Feels like a work of history to me. It's history and philosophy. Part of the reason why I say that, though, is it just covers such a breadth of time in such detail. And, he starts with Plato, Aristotle, Euclid. So basically, very much in the beginning of this trend here. He also has a chapter before that where he just discusses mathematics, beyond in various different cultures and civilizations at that time. But then he goes all the way through Frege, Bolzano, Gödel, Dedekind, and Hilbert. He doesn't really get into any contemporary philosophy of math, but again, I think this is in part because it's a work of history, and so, he kind of ends at the early 20th century. But if you're interested in the details of the history, this is a great sort of overview. It's broken up into three parts, and throughout the text, he gives many quotes translated in several languages, which is interesting. And of course, he always translates it into English. The book is written in English. But depending on who the person is and what their original language is, he almost always will quote it in that other language as well, which feels again like something historian would do. Um, you know, I can't read any of those other languages, but if I was a historian and I could read those other languages, perhaps I get a little extra insight. And he often emphasizes etymology, which again, I must admit, I'm quite ignorant of and not very interested in. But for those who have a lot of knowledge in that area, I assume that gives a deeper understanding of the history and what's going on. And each chapter is followed by a long list of references. So again, it makes it list. There's many, many chapters, and each chapter has a very long list of references. So it really does make it feel like a reference book, more than like a typical book that I might read on philosophy of mathematics. And in part one, it's entitled Philosophy of Mathematics in Antiquity, and again, that's Plato, Aristotle, Euclid, and several others. In part two, it's Philosophy of Mathematics in the 16th, 17th, and 18th century. So this is like Descartes, Locke, Leibniz, Berkeley, Hume, Mill, and ends with Kant. Again, I personally am not that interested in this kind of thing because when you read the philosophy in the second part, um, it feels very awkward to the modern ear, to like, especially the modern mathematician. The ideas feel really bizarre and not natural at all. So it's interesting from a historical point of view to see where they were at the time. It's also interesting as a mathematician to think about how these, 16th, 17th, 18th century mathematicians were thinking. It might surprise you if you're not like familiar with that. Some of their ideas are going to feel really, really bizarre. But one thing that's kind of fun from this point in time, you might remember that calculus was developed in the 17th century by Newton and Leibniz. And famously, when we look back on that calculus now, it was not written in a way that we would consider rigorous today. They used these things called infinitesimals, but they didn't really explain what infinitesimals were carefully enough for the modern, mathematician and reader to be comfortable with the arguments, right? So they were most of their arguments were correct, but it's just a little bit dangerous when you build, a mathematical theory on something that you don't, something like infinitesimals, if you don't, carefully describe what they are, you're bound to make mistakes. And famously, there are some mistakes that were made because of that. But what's kind of fun here is that Berkeley, this famous philosopher during that time period in what's called modern philosophy, he's a famous empiricist, and he has a critique of calculus, which he calls these infinitesimals. He makes fun of them as ghosts of departed quantities, right? So it's sort of this sensational way of making fun of these infinitesimals. What's interesting is that now we know how to make infinitesimals rigorous. It's not the way that we tend to teach calculus. We tend to teach calculus in the epsilon delta tradition, which was the first way that we figured out in the history of development of this, of how to make calculus rigorous. But now we know at least two ways of making calculus rigorous. There's the epsilon delta way, And then there's a way to do it with infinitesimals. But they did not use that sort of rigorous version of the infinitesimals at the time. They didn't have the machinery they needed to make that work. So that kind of history is very interesting to me. And then part three is philosophy of math in the 19th and early 20th century. So this is for me the most interesting part of the book, and it is nice like how deep he goes into it and how much of the history he covers in such a short amount of pages. In particular, what I found interesting here, and I wanted to read a little small quote, was that what we call Russell's paradox, the author actually corrects us and tells us that it should be called the Zermelo-Russell's antinomy. Antinomy is sort of another word for paradox here. So Russell reported that he found the aforementioned set theoretical antinomy, what we call Russell's paradox, in the summer of 1902, or perhaps even 1901. Zermelo had already come across this set in the winter of 1900/1901 or earlier. So he corrects us and tells us that we should be calling it the Zermelo-Russell antinomy or the Zermelo-Russell paradox. And, Zermelo is famous for, it's one of the names in the accepted foundation for set theory, for mathematics now, which is called Zermelo-Fraenkel set theory. So that first name in that ZFC is this guy Zermelo. So he is very influential on set theory. So it's interesting to be corrected now and know that it's actually Zermelo. We should maybe call it historically the Zermelo-Russell paradox. And then one other chapter I really wanted to emphasize was it's entitled "The Emergence of Structuralism," and he goes through um, Dedekind's uh, he goes through Dedekind's work, and which brought in the idea of structuralism. And I think structuralism is the philosophy that is sort of the established orthodoxy of mathematicians. We don't even know, I think, that we're structuralists. And let me just read this quote. By the structuralist view of mathematical objects, I mean the view that reference to mathematical objects is always in the context of some background structure, and that the objects involved have no more to them than can be expressed in terms of the basic relations of the structure. So I think, just crudely, according to this view, you don't talk about what the real numbers are as objects. You don't point to them or try to necessarily describe them. You can do that, but what the real numbers are is one way of talking about what the real numbers are. They are a complete ordered field, um, and up to isomorphism, there is one complete ordered field. And so, because there's only one up to isomorphism, that's what the real numbers are. They're the structure described by a complete ordered field. So I think that's a lot of way how modern mathematicians think. We don't even realize that we're structuralists by default. So it is interesting to read up where that came from via Dedekind and others, and maybe some of the philosophical issues with that particular position. So if you're interested, check this out. It is again a huge work of history when it comes to philosophy of math. But if you do check it out, let me know what you think, and like, comment, and subscribe. And I hope to see you at another video.